Hello everyone and welcome to this fourth lecture of ROS Autoware courses. Today is a little bit special as we will not talk directly about ROS and Autoware, but rather about the underlying technologies. We will cover topics such as hardware and ECUs in the car. We will cover the software topic about the operating system, kernels, and all these criteria that you will have to face at some point when you are designing and optimizing your system. And I hope that at the end of this course, you at least know the key criteria and key notions that will help you to have discussions with the low-level developers and hardware developers. After that, I will give the hand to Ricardo at AD-Link that will cover the topic on DDS. I'm very glad to be part of this initiative. My name is Stéphane Stram. I'm working as product manager at Carre, French company doing the many-core chip. And let's go into the session itself. Let's jump into the car. So let's go into the automotive ECU. Let's start, in fact, this lecture by explaining the context of the system that we will work with. And as you know, ROS can be applied to many environments, and AD-Link will explain that in the third part of this session. However, we wanted to focus these hardware and operating system sessions on the automotive applications, especially for ROS and Autoware applications. So what I will do now is I will jump into the car and explain to you that we have elements of hardware that are called ECUs, electronic control units. As you can see here illustrated on this picture, we are numbering up to 80 or more ECUs into the car. What I'm referring to here is a level 2 vehicle, which is sorting done by SAE consortium that classified the type of autonomy into the vehicle. And level 2 is from 0 to 5, and level 2 is one of these advanced assistance driving system that we are talking to and currently on the streets. So talking about 80 and more ECUs in the car can explain the complexity of this system, even if some of them are very simplistic, I would say, to manage your window up and down, for instance, up to a full autonomous driving car, in fact, that are the focus of the Autoware stack. Obviously, having such an extended systems has been growing over the years, and in fact, when we look a bit at the architecture of them, it has been done, I would say, organically as we go, and the car manufacturers have been adding ECUs and ECUs as soon as new features were coming, and the complexity of this architecture has been quite enhancing. Obviously, architects at car manufacturers and tier ones are looking at optimizing this type of architecture, and this is where the discussions are going on different new architecture views, especially functional architecture or domain architecture, where we will dedicate ECUs to different type of functionalities, as illustrated on the right, or as well an evolution going to the zone-based architecture that will be more about the topology of the car and where you will having dedicated zone functionalities at the front of the car, at the rear of the car, or other parts. That comes to the questions: how do we make all these domains or zone communicating? And that comes to this type of distributed architecture, usually highly complex, that needs to look at security, of course, and safety. That's obvious. And this is where this type of approach came to look at the ROS architecture software, because we are talking about something that is similar to other type of systems, and where ROS2, DDS, as you will see, are fitting completely in terms of features, in terms of reliability, in terms of performance. Obviously, we have to look at something in this lecture, so I will focus my talk about ADAS and AD. Two of ECUs that are coming up into the car. Some vehicles are in production with ADAS. AD is growing up. ADAS stands for Advanced Driver Assistant System, that helps you to park your car, to control and monitor your speed, to have management of radars for indications when the driver still remains in control of the vehicle. Autonomous driving, AD, is the step after, where in fact the vehicle will be able as well to drive by himself. So this is to be seen as evolution, and this is exactly how a distributed software, distributed architecture can actually really fit in order to be evolutive. So let's take a look at the ADAS and the AD functions that an ECU needs to support. ADAS and AD functions can be summarized in this sense. You need to have elements that shows you where you are into your environment. That's the sensors. Sensors can be of different type: camera, radar, LiDAR, GPS, and others, depending on what information you want to collect. Obviously, everybody understands the camera is very useful for identifying signs on the road, while LiDAR helps on understanding the environment topology, and radar can be used in other environments such as night or limited visibility as well. The combination of these sensors makes the system more reliable because more data can be fusioned. And the sensor fusion is one of the key entry points for the perception module. Perception module being more or less this step where the vehicle understands his environment, meaning being able to localize himself within the environment nearby, being able to detect the objects that are close to it, and even to track them, to classify them, to understand what next movement is possible, and to segment the environment to identify the road or pedestrian path. Combined with the map, the perception is really an environment where functions where you have needs of a large compute power, meaning, for instance, AI with convolutional neural networks for the vision and for LiDAR information. Once you know where the vehicle is, you can plan where to go. And again, with the map here and with understanding what is the road, where you want to go, what are the objects in front of you, you have these planning features, the third block, where you can define what is the safe path and predict what will be the move for the vehicle. Here, the ECU actually needs more capability of computing regarding mathematical functions. We are talking here about capability of computing matrices in order to actually identify the best road, the best path possible. So that's the path planning. And finally, with that, you have to be able to control the vehicle, meaning acting on the actuators so the direction, the speed, the brakes, in order to give instruction to the car to move. So that's in 4 blocks the summary of ADAS and AD. Depending on the number of sensors, depending on the capability of perceptions, the reliability on the planning and the control, you can move in different type of environment safely or not. It depends if you go fast on the highway with one direction, or if you go slow on a parkway to have your car parking by itself. And that's what is called use case for the ADAS and AD, and that helps defining the complexity and the performance required by the ECU. If we look at the components that are required within the ECUs, in fact, more or less, you have the sensors that inputs data. And as I was explaining, you need to fusion the data from these sensors to be able to act on the perception and planning and to do the control. That is more or less the application processors here that will be part of the ECU. Obviously, you need IOs to welcome, for instance, MIPI CSI from camera or other type of data from LiDAR, from camera, from GPS, different type of buses, different type of protocols, different type of IOs that need to feed these application processors. Processors plural because you can have, for instance, the integrated signal processing or visual processors that helps you to welcome this type of data, to format them, to be able to work with them. The application processor is obviously a powerful CPU. We see x86, Intel, we see ARMS type of processors that are running this type of applications. On top of that, in fact, as I was saying, for the perception, you need quite a lot of compute power, or even, in fact, for some complex applications on advanced driving, you do need a large amount of computation for doing convolutional neural network, object detection, object tracking, segmentation, based on image processing. And about the path planning, you need extensive compute calculation of mathematical algorithms in order to identify best options possible. What is happening today into the car ECUs is that those type of mathematical and CNN computation has been done mainly by GPUs in terms of prototyping, in terms of algorithms development. So today we do see a lot of GPUs within the car combined with the application processors. We do see as well a new type of architecture that are dedicated to embedded and dedicated to this type of algorithms, or combination of this type of algorithms in order to fit the use case I'm describing. And finally, last but not least, we are talking about a very constrained environment, the vehicle, that do need to be fully reliable, and more than that, fully safe. And there are standards around that, and I'm talking here about one, which is the ISO 26262, that is defining process of development and verification methodologies in order to ensure a level of safety, ASIL, that will monitor also the behavior of this ECU and be assessed by companies that are saying that the functions done by application, function done by the accelerators on the right, are actually safe and will do what they are expecting to do. So that's the complexity of an ECU in the car that we are talking about. That's the complexity that needs to be managed by the software for having a reliable Autoware stack on top of it. Obviously, as this is evolutive and there is a lot of separated functions, you can see a large spectrum of boards and chips that goes today into the ECUs. For the production, I'm illustrating that with the Tesla board here and the Tesla chip. For pre-production as well as for development boards, you can see different type of evolutions that are taken by tier 1s or OEMs, car manufacturers, in order to be able to think about their architecture, how it can achieve the functions I want today, how it can evolve in the future, how we can welcome more and more softwares within that. The automotive chip category I'm talking about here are these type of chips from Tesla, for NVIDIA, dedicated chips from other vendors, multi-application accelerator from as a MPPA from Calray, and safety dedicated chips for Infineon, for instance. This is what we do see today and what people are developing on for ADAS and AD functions. What is important to understand then is what are the supporting software for these ECUs. What do we need to make that running? And this is where we will introduce the abstraction levels, more or less, so different level of abstractions of the functions. You have a hardware with ECU, with application processors, safety processors, accelerators. You need a software environment that expose these different features from the hardware. And that's what we will look at as enabling this hardware with the operating system kernels. While on top of it, you will find libraries, user services libraries that you may know already, and board support package that are customization of this software for one given ECU. And on top of that, protocols and communication. So protocols as ROS and DDS, you will see that. These are examples, but you will also rely for your application on some abstraction on access to the functionality below, such as POSIX way of communicating with libraries and below features. What I wanted to say here is actually to explain that the next part of this lecture will focus on the operating system to give you the first step of software that you will need to look at for understanding how your application on the very top will be adapted to the ECU that you will work with. So that concludes this first overview of the current hardware we can find into the ADAS and AD topics. Now we will jump into the software, the operating system. You may wonder why a semiconductor company is talking about operating system, but you need to see the operating system really as the enabler of the hardware. When you will develop your system, you rely on the performance, the determinisms, the reliability of the hardware that is exposed through this type of software. Let's jump into it. To the operating system and real-time operating system. So what we will see here is first understanding or summarizing what is an operating system, assuming that a lot of you knows that already, so bear with me. What makes, in fact, a real-time operating system, RTOS, and the differences with the OS? What are the key criteria that we will have to consider into an RTOS, so you understand what are the reliable and performance and determinisms that you will be able to look at for your optimization? What are the main available RTOS in automotive? So I have a list here of companies providing RTOS that are answering those key criteria. And obviously the abstraction level that you will look at and the DDS session that Ricardo will do after that. And I will have a talk about the virtualization, as we have seen the complexity of ECUs and architecture sometimes requests more than one abstraction of the operating systems, but more virtualization. As I was saying also, why a chip maker cares about the OS. We do need, as a chip maker, to expose the features that we want to the user to use, and adopting the right operating system, the right RTOS, is a key for providing those capabilities of applying use cases, facilitating the programming of the hardware with language, with protocols, and obviously providing the features and the performance to the user. So I'm glad to be able to explain that to you from the chip maker's point of view. So an operating what? An operating system or systems, in fact, is for the user to take the benefits of the hardware and to be able to abstract the feature of this hardware, the compute capabilities, CPU, access to memories, access to peripherals. There are many types of hardwares, as we have seen, even in one type of use case, such as the AD in the autonomous vehicle. So these abstractions can be either quite straightforward, microcontroller, or very complex, taking care about different type of CPU into one chip, having different type of memory hierarchy, or taking in consideration security or safety. So from a single microprocessor, 8-bit, the operating system will have to expose less than for many core, 60 bits, 80 cores, and parallel programming. The operating system is a huge world, and I will try to guide you into some of this part of the world. What an operating system needs to achieve first is obviously to provide a memory management, so you can actually have data and programming model within your system. I/O management, so you can have access to the external data. Resource allocation, which means that you can have access to the different type of features or peripherals that the hardware and ECU is providing, helping you in understanding what error or issues are popping up into the system, and obviously providing a kernel, so or to be linked with a kernel that is taking care of the task management. So I assume that the audience here know what is a task, and what is process. The idea here is to stay at the level of task definition, where you will have to understand how tasks are managed by an operating system and how interrupts are managed by an operating system. We will go into more details that are the features of a view that, depending on your application, depending on your hardware, and how you wanted to tune it, you will have to look at the features of your operating system to make it performant as you wish. An operating system that I described can be seen on your laptop, on your desktop, on server, and that is really focusing on how a user can do programming, can watch a video, can do drawing or whatever, and focusing on performance. I need to have my application acting as my user is expecting. A real-time operating system will address other type of use case, and we'll see that. And what I think is very important to understand at the very beginning is to not to confuse speed with haste, which might be a French expression, but it is important to understand that performance and real-time might be two different concepts, and I will try to explain why. The fundamental is that the embedded system we are talking about, a car in the example I'm taking for this lecture, but the other embedded system that the next session will talk about as well, such as planes, such as robotics, such as a complex system in a city, require a predictable behavior. That is a fundamental. So if you have one thing to remember about the RTOS is that it requires predictable behavior. An OS, such as a Linux, such as a Mac OS, such as Windows, is by essence, by definition, non-deterministic, instead of an RTOS that needs to be deterministic. I will define this concept. Knowing exactly how the behavior will be if I have this type of input. Soft real-time, hard real-time are two concepts as well. Hard real-time allows you to really have boundaries of time that you can rely on. This task needs to start here and to stop here. A soft real-time gives the impression of doing things in parallel. Guarantee of time for task completion, not only giving the time, but having the task completed in expected boundaries of time, which sometimes is called worst case execution time, WCET, into our concept, and taking care about acting on external events, and that we will talk about interrupts pretty soon. That's, in a very high summary, differences between an OS and a RTOS. So deterministic, as I was saying, one key concept is the fact that you need to have a predictable behavior, and to do that you need your RTOS to be deterministic. What does it mean? It means that you need to have an interval, the time interval between your input event and your output event predicted. The system that you will rely on will have to always respond with a specified by you lapse of time. Obviously, the difficulty to make it happen is that you will not run only one task on your system. You expect to run multiple types of tasks simultaneously on different types of CPUs. So you need to be able to share the resources and the time of computation. To achieve that, you need key features that makes an OS an RTOS. Those key features are actually starting by the management of the task and the consideration of task priorities. In an RTOS, you will have those many tasks running on the system, and mainly, usually, all of them are time sensitive, needs to happen in a given time. And to do that, you will define per task a state and a priority. A state being when you initialize a task on the top left, your task will be in a state that we can summarize as being ready. I'm ready to execute. Can I execute now? This is up to the system to decide, to the operating system to decide. And the decision will be done on different type of mechanisms that I will describe. Once the task is considered to be run, you will go from the ready state to the running state, and you will execute your computation, your program. You can finish that, or you can be interrupted, meaning that another task that may have a bigger priority can request the resource that you are using and then take place of your first task and execute and being running at its turns, which means that your first task will be blocked and will wait for the next slot available. The illustration here is very simple. There are many mechanisms that are managing the states between ready, running, and blocked. I will illustrate some of them here, but what is important to understand is that as you have critical behavior to be managed in a critical time, you need, as a user, as a developer, to understand your system, to allocate the right attribute to your tasks to be considered by your operating system in the right way, the one you're expecting to. To do so, an operating system will help you. And it will help you by providing a scheduler. And the RTOS will carefully select and sequence those tasks according to the questions: what is the appropriate next tasks to be loaded, to be run on my CPU? There are algorithms for that are configurable. I will give example of the cooperative scheduling algorithm, the round robin, and the preemptive one. What you need to understand is as well that you need to know which type of tasks you have, what priority you want to your tasks, and what type of algorithms you think relevant for your use case. There is no absolute answers. You will have to do compromise. This is usually a trade-off. What we do see, however, more often into embedded system, as we are talking about, is the preemptive algorithm usage with some key criteria. Let me try to define that to you. On this page, we do see two types of scheduling algorithms, the cooperative on the left and the round robin on the right. So let me try to guide you on this path. The left diagram here shows a system that runs 3 tasks, task 1, 2, 3, and obviously an idle task, so when the system is not doing anything, which is not happening here. The axis is on the below the time. So let's assume that your system starts with task 1. The cooperative algorithms says that you are defining a sequence of execution. The easy one here is task 1, 2, 3. And once task 1 has started, it will run until its completion. And then give the end, the scheduler will give the end to the task 2 that will do the same. Start until its completion, then task 3, and back to task 1. You are ordering your tasks to be sequential and to give back the resource, so the execution capabilities, to the next task as defined by your system configuration. Each task then completes its workload in the time that it needs. And as you can see, it can differ. Task 1 is taking 200 milliseconds, 50 seconds for task 2, 80 seconds for task 3, and so on. And they came back to ready state in between because they have completed their task. That is good if your system needs to be sequential and you have an understanding about the time execution that each task is taking. And it's simple. The round robin is another approach that allows you to slice the time. So you will define a kind of quantum of time. Here 50 milliseconds. We are on the right diagram here. And we assume that we have the same sequence of tasks, 1, 2, 3. In fact, here, when task 1 is started, it will be preempted, meaning stopped by the operating system after 50 milliseconds and go to the block state that we were talking about. So task 2 can actually start for the next slice of 50 milliseconds, and so on with task 3. That allows you to define a system that is very time-driven, and meaning that you give to a task a fixed amount of time to execute, and you control like this the fact that you will be able to know the period of execution of tasks. As you can see here, and I think, yeah, for instance, task 3 has been blocked after 50 milliseconds, and task 1 is taking the resource, and when the next task 2 is preempted to finish and to give the hand to task 3, task 3 can here finish and complete his execution and go back to ready state. So that's a way to configure an operating system. This is the round-robin scheduling algorithm. The last one I want to address here, and there are many ones, by the way, is the preemptive mechanism. Preemptive takes almost the same concept, but adds the priority management of the task. In this example, task 1 has the highest priority, task 3 has the lowest priority. And what I'm illustrating here is that, let's say the system is running task 3, and task 2 needs to act, needs to run. As task 2 has a higher priority, it will block task 3, so put task 3 in the blocked state, take the lead and execute. It happens that task 1 requires the resource, and so task 1 with a higher priority will as well block task 2 until its completion, and then task 2 will resume until it is ready and give back the end to task 3. That will be blocked as well by task 1 at some point until it's complete, go to idle state, and task 1 is interrupting as preemptive as well idle state. It can be very complex when you have many tasks, several levels of priorities, but I'm sure you see already one of the big advantages of this scheduling algorithm, which is the fact that you can ensure some periodicity for task execution. Here we can imagine that the task 1 is triggered by a number of ticks or clock cycle, and that task 1 need absolutely to execute every X milliseconds. Thanks to this type of scheduler, you can ensure that task 1 will always be executing when you expect it to be executed. That could be for monitoring a system, that could be for ensuring a bit clock, that can be for many reasons, but you are ensuring this type of behavior, a strong determinism behavior for your system design. In addition to that, in fact, we have interrupts. An interrupt will break the sequence we have seen, the sequence of operation. Again, you have interrupts levels as you have task priorities, so you can control that and ensure that this set of interrupts are not interrupting this set of tasks, and so on. This, as you can imagine, can become quite complex. You have external interrupts, you have internal interrupts. When an interrupt occurs, in fact, you will stop a task. So you will suspend its execution, as we have seen. You will have to save the context of this task to make sure that you go to the interrupt handler, which is the code that will be executed and should be very fast to not block the entire system. You process this handler and you go back to the task that you interrupted. Some definition around that, but I'm sure now you have with the scheduler algorithms a good understanding about what I'm talking about. On the top here you have in blue the execution path, so this is a task that is executing, and you received an interrupt, maybe an external driver that an external peripherals that the drivers generate an interrupt to have an action. You then save the context, jump to the interrupt routine, restore the context, and go back to the execution. Depending on your hardware, depending on your operating system, you can have different response time on such interrupt. as I'm insisting on this predictable behavior and these determinisms, it's very important to understand this time calculation here for the latency between the generation of the interrupt and the start of the management of it, so the start of the save of the context. The time that is required to save the context and to restore a context, that can be very different depending on your operating system, and obviously the overall time of execution for your routine. You can understand that if you put a lot of computation within the interrupt routine, you are breaking your task sequence, and it's highly not recommended. You have rules around that you can go into details as well. But with these notions here of interrupts timing, you as well understand how to deal with tasks and interrupts within your system. Another very important topic is the memory management. Obviously, this is critical. If we take an example of memory allocation, and if we take the example of Linux, for instance, as soon as you access memory such as RAM or disks, you can generate a page fault that avoids the system actually to run out of memory. But during a page fault, you are holding the computation to load this missing page, and this is unpredictable. So it's not good for real-time operating system. Dynamic memory allocation is very similar, and because you can create memory fragmentation, and so resulting into an unpredictable amount of time to allocate the next bunch of memory, for instance. Again, it is the memory allocation and page fault is a very good system. The dynamic memory allocation is a very good system for some use cases. For others, we need to manage that in another way. In RTOS, you need to avoid page faults, and you must manage your memory allocation very carefully. An RTOS will do that for you. I will not describe the different mechanisms here because there are many, and depending on the RTOS that you will select, I will give you a list. You will have different type of memory management, but mainly you have dedicated mechanisms. You can pre-allocate memory, you can have static allocation per task, you have dedicated API to manage these things, you have semaphore, and you have also monitoring and debugging capabilities as soon as you see that your memory allocation impacts your timing. A slide here that you will have access to is an example from a real-time background on the design ROS2 that I found very interesting, saying that you can actually work with Linux in a close enough type of memory management for real-time, having lock memory, pre-fault stack at the top here, as well as a way to allocate dynamic memory pool, which is mostly providing real-time allocation, but where you have constraints you actually need to be very careful with to predict the bounded memory size, so your process is executing into these boundaries. You need to take care about STL containers and trying to have as small as possible, to keep as small as possible the memory footprint for your processes. But that's a very good way if you want to practice and if you want to understand the impact of managing memory for real-time system, to work with Linux directly. Another topic that is important and that you will face when you will select or work with an operating system is to understand the way the operating system is dealing with its own kernel. You have two big families. You can see differences, but there are two big families: the microkernel approach and the monolithic kernel approach. The microkernel, more or less, is differentiating the user services memory space from the kernel server memory space. user services and kernel services are not sharing the same address space. The monolithic kernel, the reverse, is sharing the same address space between user services and kernel services. Kernel services being the memory management, the scheduling management that we were just talking about, while the user service are the exposing those libraries and API up to the application. So that's the way to see this difference here between microkernel and monolithic kernel. Let me give you the main differences here. Microkernel on the left, monolithic kernel on the right. In terms of size, obviously a microkernel is smaller than a monolithic kernel. That's obvious. In terms of execution, it can be slower than a monolithic kernel. So monolithic kernel being faster than microkernel. And again, I was starting that lecture with this sentence, not to confuse speed with haste. It's not because you are real-time, even hard real-time, and deterministic, that you are fast. This is two notions that I think now you understand. I want my behavior to be predictable and to manage the time. Doesn't mean that I need to run fast. Usually the constraint is that you have to, but that's something you have a trade-off with. Stability. A microkernel will be unaffected if there is a service crash because we are not sharing the same memory space. Obviously, a monolithic could be more easily. Extendability, because you have in separated space, it's facilitated into microkernel. It's a bit more complex in monolithics to be maintained. The debug capabilities is usually set more easiest on the microkernel and more complex on monolithics. I think it's arguable. It really depends on the RTOS you are working with or the OS you are working with. So I report that, but I do say this is arguable. And some examples, so microkernel examples of commercial OS are QNX from QNX, Integrity and EMCOS from ESOL, and obviously as monolithic kernel you have Linux, BSD, and others. When you have a type of resource such as CPUs, you may have different type of CPUs into one ECU. Different type of CPU into an ECU. You will have diversity of hardware, potentially diversity of operating system, one operating system by CPU. A lot of devices to be shared between the application running on top of that and taking care about safety and security, of course. To do that, there are main concepts that are managed by operating system or above, we will see that, is the spatial isolation, a mechanism to partition the access to the resource. It's memory partitioning, to make it short. So you allocate memory partitions and CPUs to your execution. And temporal isolation, which means that you are giving a resource for a given time to a task or an application, as we have seen before, spatial and temporal. There are many mechanisms for that. I'm illustrating 4 of them here. You probably know the hypervisor type 2, which on top of your operating system, let's say Windows, is adding an hypervisor, let's say VMware, that is welcoming different type of OS and application and taking care about sharing one hardware, your laptop. That's very flexible, mainly used in server and desktop, and very could be costly to deploy. And the abstraction is very high in terms of sharing the features, and in terms of determinisms, it's limited. That's why there is an hypervisor type 1, which is called the bare metal hypervisor, which in fact is a kind, we can say this is a kind of operating system that is taking care about spatial and temporal isolation to share the hardware with OS, but it's very down to the hardware, mainly used in embedded system, usually dedicated, as you can understand, to this type of CPUs that is managing, and quite complex to configure and quite complex to maintain. Not even talking about security and safety. New concepts are popping up, such as hardware spatial isolation. Your hardware is actually providing you all the benefits of sharing resources in terms of spatial access. So it's easiest to configure and to maintain, as well to certify, and mainly taking care about MMU and MPU, memory protection unit, and hardware element as an hardware element that is directly usable by an operating system. And you have tools to program, in fact to design, to program, to monitor and to debug your temporal isolation. An example is an OS that is provided by Chronosafe, which is called Asterios, that helps you to, as illustrated here, taking care of all the timing that we have seen in the beginning of this presentation. I'm just illustrating this new concept here with an example of on-chip many-core, where you have the capability of running performance OS in part of the chip and determinism execution on other part of the chip. As you are managing the memory allocation, you are managing the communication with dedicated communication fabric on the chip, and you are sharing up to 80 CPUs in memory space protected. So the operating system can more easily taking into consideration spatial isolation and having multiple type of application running on one CPU, which can combine application for an ECU. Hard real-time dedicated on determinisms on one part of the chip, here 16 cores, with temporal isolation taken care by a dedicated OS. Running a rich OS or RTOS, such as even Linux on OS or EMCOS or Integrity, and having, as we have seen before, these needs of acceleration. Here taking care about the dedicated accelerator for CNN and for mathematical acceleration that can be accessed by memory. Finally, some example of the RTOS in automotive that are covering the aspects that we have seen all together here. I'm listing the biggest one. Sorry for those I forgot. Please comment here to be listed. So the company providing that are QNX BlackBerry with their QNX Autos, Wind River providing the VxWorks, Green Hills with Integrity, Mentor Graphics Siemens the Nucleus, eSol is providing EMCOS and its variety, Chronosafe the Asterios I was talking about, and Cisco coming from the avionics and into the automotive with his real-time OS Pike OS. Your focus as a developer of application or developer of ROS system is really to understand what is below. That is the main aspect here. So what is the use cases that you are willing to implement in which system topology, ECUs, CPUs, accelerators, the determinism strategy you need. For some of your ROS nodes you will need full performance. You don't really take care about determinism. For some others you will have to, and so you need to define the strategy. Select your hardware or take the hardware that you have or you have access to, and the RTOS similarly, and start to map your topology to your determinism strategy with the capability of your hardware and your RTOS. Define your tasks carefully with priorities and your scheduler methodology you will have. Take care about the interrupt configuration and enjoy working with these all tools. I would like to thank you for your attention. I give the hand to Eddie Link, and stay safe. And that is concluding our sessions on the hardware and operating system. I hope that I raised your curiosity, I maybe refreshed your mind, or at least I provided some key notions that you know you will have to look at for an appropriate design and optimization. Looking forward to hear about your design. Do not hesitate to contact the Autoware Foundation and the working groups that may help you to go deeper into these technologies and into your system. Thank you very much. Bye.
Hello everyone, I'm Angelo Corsaro, ADLink's corporate CTO. In ADLink, besides typical CTO activities, I run the software R&D and the DDS business unit. I've been involved with DDS for a very long time. Virtually since the very beginning, I've been contributor to all DDS standards, and today I'm here to introduce you this very interesting technology. So what we'll do, we'll try to introduce the very foundation of DDS, look at some of the advanced concepts, and then more importantly, look at the features of DDS that are specifically relevant for robotics and in general distributed real-time systems. So how about we get started? So here we are, let's get started. So what is DDS? Let's try to define DDS in just 131 characters. So if we were to do so, very succinctly, I would say that DDS is a standard technology for ubiquitous, interoperable, secure, platform-independent, and real-time data sharing across any kind of network-connected device. So I think this very, let's say, in a way dense, but at the same short definition, capture the essence of DDS. So let's look at DDS as a standard to begin with, and more importantly, let's look at how the standard has evolved in the past, let's say, 15, 16 years. So DDS as a standard was introduced in 2004, that was back then DDS 1.0. In 2006, there was a major addition because when it was first introduced, DDS was just an API standard. There wasn't a wire protocol. In 2006, we standardized a wire protocol which was ensuring not just application portability, which is achieved by means of standard API standard, but also on-the-wire interoperability. 2007 saw a revision of the DDS specification, and then between 2008 and 2010, there were some major revision of the DDS wire protocol, landing in 2010 to version 2.1, which I would say is roughly the major version that has been there for the past 10 years. 2012 to 2014-15 were rather active years. Why? First of all, we extended the type system of DDS, as we will see, by allowing for type extensibility, and I'll explain a little bit more in a moment. We refreshed the programming language API. The original C++ API for DDS was rather error-prone and I would say cumbersome. If you look at the new API that leveraged C++ 11, 14, moved semantics, and iterator, it's far more type-safe, efficient, and I would argue a pleasure to use. DDS was expanded with security in 2014, and in 2015 we divided actually the DDS specification into DDS, which used to be what we called at some point DCPS, so the data-centric publish subscribe, and DLRL, which was the data local reconstruction. So, up to DDS 1.3, let's say, DCPS and DLRL were part of the DDS standard. Eventually, DLRL was pulled out in 2015, and it's a specification we are not maintaining anymore. We introduced also DDS RPC, which was eventually, let's say, nailed down 2017, and 2019 and 2020 have seen another update of the DDS RTPS version 2.3, so sorry, there is a small type in the slides, as well as a major upgrade of X types addressing some of the type checking and some of the metamodel matters. So how does the DDS standard looks like? So first of all, if we go bottom up, the bottom layer is the wire interoperability wire protocol. so DDSi RTPS, and this sits on top of an IP transport, which could be UDP, or eventually, I think we'll standardize the TCP transport. So there is still some work being done. It's not there yet. Essentially, all the vendors support TCP/IP, but that's not part of the standard. So this is equivalent of a layer 5 in ISO OSI model. And again, it is the bulk of the DDS implementation. It is also what guarantees wire interoperability. On top of this, we have the DDS layer, which provides you with abstraction for the DDS primitives and API for those. And then aside, we had other specifications like RPC, security, X types, and so on and so forth. So if we look at the X type standard, as I mentioned before, it was a major innovation for DDS because the DDS type system used to be nominal. So in DDS, two types to be compatible had to have the same name and had to be identical in structure. Going forward with X types, the DDS type system was changed to become a structural type system. DDS security is another important addition to the DDS family as it provides a pluggable or let's say plugin based security infrastructure to control, among other things, access control, authentication, crypto, and logging. So because of a plugin-based architecture, you can plug your crypto, you can plug your access control, and so on and so forth. But of course, there are some default plugins, mostly based on PKI infrastructure. So to conclude, in terms of review of some of the key standards, we have the DDS RPC. So DDS RPC adds remote procedure call on top of DDS, and in a way, I would say that gives the ability to people to use traditional client server on top of DDS. Should you use it? Well, again, I think it depends on perspective. As we will see, one of the main advantages of DDS is to promote data centricity and decentralized, decoupled, distributed system, and a design that makes it relatively easy to build fault-tolerant distributed systems. And more importantly, to have very little coupling, also in terms of temporal coupling. If you start using RPC on DDS, all the issues that come with those kind of technology, in a way, you bring them back into your application. So I always warn against the use of RPC. I think it's much better to have an entirely data-centric design because overall, it makes it much simpler to reason about availability, fault tolerance, and other important properties of distributed systems. So let's look at who uses DDS today. So DDS is extremely used in lots of different application domain. So for a few years, it has already been used at the foundation of autonomous vehicle in agriculture. So as you know, there are today several different classes of autonomous agricultural vehicles, from harvester to combiners to several other, and many of those are indeed powered by DDS. Smart cities have been adopting DDS for over 10 years now. The same is true for smart grid. There is even a Department of Energy recommendation that requires the use of DDS for next generation smart grids. Smart houses around the world use in order to do monitoring and control use indeed DDS. Then we have quite a few uses in combat management system. The Kennedy Space Center launch system is based on DDS, and in fact, it's actually an N version program system, two of which are running on DDS from two different vendors. Air traffic control around Europe is actually standardizing on DDS, and we have some very interesting next generation simulation infrastructure built by NASA, namely the NASA Smart NAS, which is also powered by DDS. Unmanned air vehicle have been using DDS for quite some time, initially in the control station and now incrementally also on the UAV. Very complex simulator, both for helicopters, for airplanes, and actually even for driving cars. most of the time when you need hybrid simulation, they use DDS. Smart factory is another example. And something that it's quite impressive for me is the extremely large telescope. In this system, DDS is used to control 100,000 mirrors that are adjusted 100 times per second. So you can imagine the volume of data. Medical devices have adopted DDS quite heavily, and you can find DDS in MRI machine, in pulse oximeters, and so on and so forth. And last but not the least, obviously, robotics. ROS is one of the capital example of adoption of DDS, but it goes well beyond, because even in the commercial world, there are several different robotics vendors that have created their own infrastructure on top of DDS. So after having seen how many applications of DDS there are in the market, one of the questions might be, okay, so but why are these applications using DDS? I think the reason are multiple, but I will try to give you with a key point. So first of all, DDS provides you with some very high level and powerful abstraction, as well as a very strong infrastructure to build modular distributed systems, which is very important for these kinds of applications. Now, because of the primitives that DDS provides you and the abstraction that DDS makes available to architects and programmers, it makes it easier to solve some of the very hard distributed system problems, such as fault tolerance, scalability, and asymmetry. So with asymmetry, I refer with system where you have a relatively important difference in computing capabilities between the nodes that make the system, in network latency, or even network bandwidth. And then you can look at DDS like some kind of universal glue that allows you to seal together highly heterogeneous environments while maintaining just one and a single extremely elegant abstraction that allow you to very effectively share data among these systems. So DDS is platform independent, so it can run on a plethora of different platforms from Linux, Windows to Android, macOS, as well as embedded platforms such as VxWorks, QNX, and so on and so forth. And you can program DDS with several different languages, so in a way it's polyglot. So most vendors provide API for C, C++, Python, Java, Scala, and so on and so forth. So let's move now to the DDS foundations. The key idea behind DDS is that of a virtualized data space in which application can autonomously and asynchronously read and write data enjoying spatial and temporal decoupling. What do I mean with spatial and temporal decoupling? Well, it means that essentially I don't need to know if there are applications interested in the data that I'm producing, if there aren't at all, or how many there are. And the second point is that the production and the consumption of data are decoupled in space. So as a consumer, I can consume data that was produced by producers that potentially are no more in the system. So the data that is produced and consumed is modeled by means of topics. So a topics represent a domain-wide information class, and it's identified by a tuple or a triplet with a name, so the topic name, the type that represents the information associated with this topic, and the quality of service that captures the non-functional properties of this information flow. So as we saw, DDS allows you to decorate topics and, as a matter of fact, also data producer and data consumer with quality of service. Quality of service allow you to express in a programmatically manner temporal as well as availability constraints for data. So that's quite unique because in many other technologies you have no way of expressing in a very direct and programmatic manner the non-functional of your data stream, while in DDS you do that by means of QoS policies. Another very important feature provided by DDS is that of dynamic discovery. So those of you that have used DDS realize that you don't need to provide any specific endpoint of application that need to communicate with each other. They get to discover mutually and transparently. More importantly, dynamic discovery isolates your application from the network topology and the connectivity details. And that's quite important for making it independent of the specifics of your deployment. Other important point is that the conceptual global data space that DDS makes available is actually decentralized. So there is no single point of failure, neither a single point of bottleneck. And the way in which this global data space is implemented is really by means of a collection of local data space. What you should think of is that conceptually there is, yes, indeed, this global data space, but then the way in which it's implemented is that the data that you're interested in that lives in this virtual data space is then projected into your local global data space, which is implemented by means of primary and secondary storages backends. Okay. Other important point is that the connectivity between producer and consumer is dynamically and managed by dynamic discovery. So depending on how you are, what are your connectivity properties or the connectivity properties of a given application, dynamic discovery can decide what is the best way for an application to communicate with interested parties. So let me give you a very concrete example. Suppose that at some point in time there is an application producing data and there is a single application consuming data. In that case, dynamic discovery might decide that the best way to communicate is through unicast. Now, suppose that a second application arrives that is interested in the same kind of data. If the dynamic discovery finds out that both applications can be reached through a common multicast IP address, okay, then communication will switch from unicast to multicast in order to optimize the network utilization. So all those kind of optimization are done online and continuously by the dynamic discovery that is built in DDS. It's now time for our first laboratory. And in order to do a laboratory, we need a DDS implementation. As a DDS implementation, we will use Cyclone DDS. Why Cyclone DDS? Well, as I've explained in the beginning of this video, we have been involved with DDS since the very beginning. We have been there, we have done that for the past 20 years. And what we wanted to do with Cyclone is really to capitalize all of what we have learned in these 20 years, capitalize from the news that there are in terms of hardware, networks, and application domain, and start from scratch to build the best DDS implementation ever, and to do it completely in the open, working with the community. Okay, why? Because we want to make sure that everyone who should be using DDS can do that by leveraging open source. We want to leverage user-driven innovation, and we want to make sure that we can continue to grow and innovate in this technology by receiving as much feedback, contribution, and interaction with an open community as the one that we have at Eclipse. So we want Cyclone to become really the go-to DDS implementation for all of those interested in using DDS. So what we will do in the next few minutes is actually to check out Cyclone, build it, and write our first example. The example that we will use is that of a generic utility appliance that might be producing electricity, gas, or water. And in fact, it's a connected meter, let's say. Okay, so here you see the declaration of the topic type and the data producer in C. So you see we create a domain participant, we declare a topic, we define a publisher, we create a data writer for the given topic, and then as this is a smart appliance, a smart meter, periodically we read the meter and write it on DDS. The reading side is rather symmetric, so obviously the topic type is the same. We have similar declaration for domain participant because, as we will see, that gives us access to the DDS domain. We declare the topic that we are interested in this case in consumer, a subscriber, and the data reader for the given topic. And then here, what we do, we just issue one read, and then using the standard for each, iterate through the samples that we have received. Okay. Again, I will show other way in which you might coordinate with DDS, either to wait for data to be there or to be triggered when data is available, because all those mechanisms are there. Okay, so at this time, we need to switch to the console. Okay, so it's time for our first demo. So first of all, you should get Cyclone. You can get it out of GitHub. So this is the URL. This is the project, the main project page, and there are very detailed information on how to install it and the dependencies that you have. I have it already installed on my machine, so that's kind of handy. By the way, if you want to run C++ project, then you will also have to install the C++ API, but you have information on our repository on how to do that. Okay, so let's get started by looking at our IDL file. So as in the slides here, we have a module tutorial, an enumeration that defines the kind of utility, and then the type for our meter. This is the CMake list file that you can use to build, as I will show you the example. Okay, so just specify the IDL file that you need to compile and in which library you want to link then the generated code. Define your executable, then we will have a writer and a reader, and then actually tell CMake to link your executable with the helper libraries. So let's look again quickly at the code. So here we have our writer. So I have a utility library just to generate the meter data, but besides that, we create the domain participant here, then we define the topic, the publisher, the data writer. Everything is with default QoS, so we don't need to define explicitly. Then I read the meter and I write. Okay. Likewise, on the reader side, quite dual, so the steps are similar, in some case dualistic, so up to the topic is exactly the same. Then I define the subscriber, the reader. Notice that the type of the reader and the type of the topic need to conform, so in this case they are exactly the same. And then within a loop in which I sleep 1 second, I read with a loan, so in a way I'm loaning memory from DDS in this case, which will be released each time I iterate, okay, and then I go through the samples and print them. Okay, quite straightforward. So let's do this from scratch. So actually, let me clean. What you would typically do, you would create a build directory. You would run CMake, so that configures, then make, and at this point we will be able to run it. Okay, so let's start our writer in this console, and let me start our reader in here. Okay, yes, of course, because that's so let's run our reader, and you will see the data being produced. So in this case is the, let's say, liter per seconds of water sensed by this smart meter. Okay, so something else I want to show you real quick is that there are multiple ways of writing your samples as well as multiple ways of reading. But for instance, you can also use a streaming operator. So we could also do like this, and things still work quite nicely. So if we start our writer and then our reader, you see that everything works. Okay, so that's as much as I wanted to show you. Let's get back to our slides. Let's try to go one step further with DDS. So what we saw is that topics are used to define the information that you want to share between producer and consumer. In other terms, data writers and data readers, if we use DDS terminology. We also saw that topics are identified by a tuple composed by the topic name, the topic type, and the QoS. Here we see as an example a light bulb in which we have the serial number, which is string, the luminosity, the U, and a boolean that perhaps represents if the light is on or off. Something that we have not discussed yet is a concept of instance. So in DDS, when defining a topic, you might mark some of the associated types attributes as being the key fields. The consequence of this is that for each unique key value, then you identify a topic instance, and each topic instance has associated with it a FIFO ordered stream of samples. So if for a moment, as we saw in the previous slides, we look at the annotation at the tail of the struct, which says pragmatic list light bulb um, state serial number, then that means that the attribute serial number is the key, which means for each unique serial number, we have a topic instance. So in this case, for instance, if you think a three physical distinct lamp, they will have three different serial number, and as a consequence, those would be three different instances, each of which with its own stream of samples which are indeed FIFO ordered. This is very important to understand, and an analogy we can make, I'll give you another in the next slides, is that of a topic identifying somehow a class of information and then instances being essentially instances of this class. DDS gives you a series of tools to also deal with instances life cycle. So you can detect that the new instance appeared in the system, or that an instance is no more relevant and thus is disposed. And at the same time, DDS also deals with the demultiplexing on instances. Okay, so you are able to read by instance, for instance, or to write by instance, obviously. Okay, another way of looking at topics is the relational perspective. So in a way, you could think of topic as defining relations. And again, here I mean relations in the sense of relational algebra. So if we go back to our light bulb state topic type, as the serial number is the key, we can think of this as defining a relationship in which obviously each row of this relationship will identify a DDS instance. Okay, so I think this is probably the best way of thinking about a DDS topic, with the difference, right, that in a typical database, as we will see, a relation identifies a table. In DDS, this table can become a cube. Why? Because we have another dimension, which is time, and we can actually, as we will see, keep track of historical events up to a certain depth, or perhaps all the values that were written for a given instance. How is information scoped in DDS? Well, all information within a DDS system lives inside a domain, and domain cannot be crossed unless obviously you join multiple domains and then have an application that bridges data between domains. Domain can be organized through partitions, okay, and then whenever you write a sample belongs to a given topic instance, right, associated to a specific topic, which is going to be read or written into one or more partitions. So that's how DDS information is organized. Let's take a look now at the various entities that you have to deal with when building a DDS application or a system based on DDS. So the key entities, as you see in this slide, are the domain participant, publisher and subscriber, data writer and data reader, and then obviously you have the topic and the domain. So some of the entities in DDS control where data is written, while others control which data or what data you're going to read or you're going to write. Specifically, the domain participant gives you access to a domain. Okay, publisher and subscriber relate to where you write the data, because as we will see in the matching logic of DDS, it's through the publisher and the subscriber that you decide within the given domain that you're associated with in which partition you're going to write or read the data. And finally, the data reader and the data writer relate to what data you write. Why? Because it's through the data reader and data writer that you write samples belonging to topic instances. DDS QoS policies control to a very large extent how the data is shared between the communicating parties, and QoS also allow you to control resource usage. So what is the matching model the DDS provides you? Well, in order for a data reader and a data writer to exchange data, as we say often in DDS jargon, they have to match. So what does it mean? Well, it means, first of all, they need to be in the same domain, which means that the domain participant that owns this data reader and data writer has to be associated with the same domain. Then, as you see in this diagram, a data writer, in a way, is created starting from a publisher. So, likewise, a data reader belongs to a subscriber. So, in order for a data reader and a data writer to be able to exchange data, then the respective publisher and subscriber have to be associated with a set of partition expressions that are matching. Next point is that obviously the data writer and the data reader have to be for the same topic, and then their QS policies have to match in the sense that the QS provided by the data writer have to match or exceed the QS requested by the data reader. Just to give you an example, if a data writer, let's do the other way around. If a data reader wants to receive the robot position topic reliably, then it will only match a data writer that provides that topic reliably. It will not match a data writer that provides that topic in a best effort manner. Why? Because the QS provided by the data writer doesn't match nor exceed the one requested by the data reader. Vice versa, a reliable writer for the robot position topic would match a reliable reader for the given topic as well as a best effort reader. DDS also has, in a way, a storage model. You should have already guessed this when we discussed the global data space and the fact that indeed it's a decentralized data space. So each data writer and data reader has associated a sample cache. In a sense, what DDS does is to take the content of a data writer cache and eventually project this content or the relevant portion of this content into matching data reader caches. As a consequence, both writes as well as reads in DDS are always local and non-blocking. There are only some rare cases in which a write might block up to a given timeout, which is when you're running out of resources. But all operations in DDS by default are non-blocking and they are all local operation. You have to think of DDS as having writers writing the local cache and then having an alignment protocol that aligns this cache, projecting the relevant content on matching reader, and data reader just reading the local cache and taking out data in the most appropriate manner. And what are the appropriate manner of taking out this data? Well, you might be interested in receiving all data, or perhaps you might be interested in receiving just a subset of data, and you might want to control the data you receive based on some specific properties or predicates on the content. So there are two different ways of controlling data that you receive that DDS provides. One is called content filtering, and content filtering controls the data that gets inserted in your cache. Okay? You have to think of content filtering as a predicate that logically looks inside the data. If the data that you're receiving or the sample you're receiving matches the predicate, then that data is inserted in your local cache, otherwise it's discarded. And by the way, this predicate could be evaluated on the receiving side or on the sending side. Okay, so here we have an example in which, for instance, you are writing an application that has to flash cars that are running faster than the speed limit. So obviously in this case, why would you ever want to receive data for cars or speed doesn't exceed the speed limit? So you could indeed express this through an SQL expression. So in this case is the equivalent of what you would put in an SQL where clause. And look that what we are requesting is for data for which the velocity on the X or the velocity on the Y direction is beyond 50, let's say, kilometers per hour. Okay? Important to understand that in this case, although the data is being produced by the car, okay, in the application that needs to decide if to flash a given car or not, only the data that matches this predicate is being received. So that's how a content filter works. Something else that DDS provides you are queries. So queries don't control what gets in a cache, they control only what gets out the cache. In other terms, you can query the cache by providing once again a predicate expressed as a where closed in SQL 92. And in this case, you see that we are receiving all the samples for the various instances, but then we are asking DDS to only give us out of the local data that matches our predicate, which again identifies either the speed on the x or the y direction to be greater than 50 kilometers per hour. Okay, so let's look now at a few other interesting properties of DDS, such as stream durability. What is stream durability? Well, first of all, stream durability relates to which data will be available and under which circumstances for how long. In a way, we could say that stream durability controls the temporal decoupling. So this can be controlled by means of a QoS, which is the durability QoS. Okay, and again, it allows you to decide, if a data is volatile, so after you have produced is gone, or if perhaps you are able to essentially provide to late joiner the last sample, the last end sample, or perhaps all the samples that you have written. And once again, this is controlled by a QoS called durability. So volatile durability essentially won't make available to late joiners any data. So what you see in this marble diagram, you see that we have a source producing data, a sink receiving data, and then a late joiner that arrives, but the late joiner under these circumstances will only receive data that is produced after he has joined the system. Now, if you use transient, let's say local, transient, or durability or persistent durability, then in that case you have real temporal decoupling, which means, as in the second marble diagram, okay, that when a late joiner arrives, he will receive the data that was produced before he was in the system. How much of that data will be provided depends on the specific settings. As I said, could be the last value, the last end value, or all the value. And then whether this data will be provided even if the sink is gone depends on the specifics of the durability settings. So for instance, transient local ties the availability of data to the availability of the producer, while transient and durable decouples completely the availability of data to the availability of the producer. Other important point that DDS allow you to control is the stream reliability. So in DDS you can have best effort reliability, in which case DDS will deliver an arbitrary subsequence of the sample that we have written for a given instance. Okay, so as you see in this diagram here, samples may be dropped because of network loss or just because of local network DDS flow control. Okay, so that's the contract that we comply or sign off when you ask us to have reliable best effort reliability. Then you can have last end value reliability. So last end value reliability is typically what you get by default when selecting the reliable reliability in DDS. In fact, there are a combination of QoS that allow you to get TCP/IP-like reliability. Okay, so last end value reliability it's quite an important concept, and what it ensures is that under stationary condition, okay, you will receive the last end sample that were written for a given topic instance. Okay, samples that fall outside of the history might be dropped on the sending or on the receiving side for flow control. It's important to understand this kind of reliability because if you're building systems that are real time, if you're building systems that in a way have to behave properly under temporary asymmetry, you want this kind of behavior. Some of you might have heard about this, the circuit breaker pattern for slow consumer, where that's actually what this implements. Okay, but this also ensures that a reliable writer will never have to block, because in any case, if a reader is unresponsive, as far as he can keep the last end sample that he has written, That's what it will deliver and will comply with the contract of last and vital reliability. If you want to have TCP/IP-like reliability in DDS, okay, which means all the samples that you write are received, then you have actually to combine two QoS. You have to have reliable reliability and keep all history on the writer and on the reader side. So that will ensure that every sample that you write on the writer side will be received by the reader side. But I think you have to use this very carefully. And most of the time, if you want to be tolerant to system asymmetry, it's much better to use the last n value. Additionally, if you design properly your data model and you try to have a data-centric, state-oriented system, typically last n value reliability with n equal 1 most of the time, or n equals to some relevant k for your application, is typically sufficient. When you want the TCP/IP-like reliability is mostly for rare event like alarms and so on. But we'll discuss this toward the end of the presentation when I will be providing you with some QoS patterns. DDS provides also some mechanisms for fault tolerance and fault detection. So more specifically, DDS allows you to detect failures like typical crash as well as performance failures. So failures are detected by means of liveliness policy, and performance failure can be detected by means of deadline policy. And in fact, it's a combination of the two that allows you to deal both with crash as well as performance failure. By the way, a performance failure is a situation under which a producer is not producing data with, let's say, the period that he had committed to. Okay, so these QoS allow you essentially to replicate producer and then have the infrastructure automatically switch between one producer and another when either a crash or a performance failure is detected. So quite powerful. So let's look at the QoS that DDS provides. So DDS provides with over 20 QoS. So sometimes people are a little bit frightened by the many knobs that DDS provides you. But the reality is that if you abstract a little bit and take some distance from this QoS, they actually compose quite nicely to support some very common idioms and QoS modeling patterns that I'll show in a few slides. It's important to understand that some of these QoS are immutable. So once you've set an immutable QoS on a DDS entity, you cannot change it. Okay. Some of them are local, so they don't impact any end-to-end behavior, and other, mostly QoS that impact end-to-end behavior, are request versus offered. So here you have the list of QoS that are request versus offered. So you see, for instance, durability, destination order, reliability, and I just gave an example before, deadline, and so on and so forth. Now, for all QoS that are RXO or request versus offered, as I mentioned previously, in order for a data writer and a data reader to match, the QoS provided by the data writer have to match or exceed the QoS requested by the data reader. Let's take a look now at some of the DDS specials or some of the DDS features that are specifically relevant for robotics. Well, first of all, I'd like to point out that DDS and robotics is actually an happy marriage. They match very well. Data centricities and support for decentralized architecture matches, and data-intensive architecture matches very well. Any kind of control application typically has to do with filtering, and if you are familiar, for instance, with FIRs, so finite impulse response filters, typically they work on TAPs, so the last n samples of a given, let's say, time variable, temporal variable. And in this case, it's very easy with DDS to maintain those last n sample through some trivial QoS settings, for instance, history QoS. DDS allow you to control real-time behavior. Okay, you can set deadlines, you can detect performance failure, you can have replicated sources that are automatically switch over thanks to the liveliness. And more importantly, many of these non-functional properties can be programmatically expressed by means of QoS. Now, some of the QoS that are, I think, particularly important for robotics application are those that allow you to control the temporal properties. And there are 5 QoS that allow you to control throughput, latency, and the trade-off between the two. For instance, if we look at throughput, inbound throughput can be limited by using time-based filter. So in that case, you can limit literally the minimum inter-arrival time of data. The trade-off between throughput and latency can be controlled by means of the latency budget. A latency budget of 0 means always send data on the network immediately, which means optimize latency. But sometimes that is a detriment of throughput. So latency budget allows you to decide whether you want to exploit some temporal locality to pack up bigger packets and send more data on the wire at once. And then you have deadline and transport priority that allow you to either commit with the period with which you are going to produce data or the period with which you want to receive data, okay? Or perhaps assign priority to data that can be used to do end-to-end priority preservation, or ideally, if you're running on a transport like TSN, map that topic priority into the proper TSN schedule. Then you have the QoS that control data availability, and there are 4. Lifespan that decides when data that is considered stale is collected, garbage collected from the system. Then you have history that allows you to decide how many samples for each instance you want to keep in your cache, and durability, as we saw briefly, that control the stream durability. So am I going to provide data to late joiners? Is this data going to be available even when the producer is gone? Then last point is the reader cache. You can control the reader cache, okay, and that's important for resource management. Once again, through the history to decide how many samples you want to store, through resource limits, okay, that allow you to control how much memory this cache is going to take, and you can also control the garbage collection of disposed instance by means of data reader lifecycle. Last but not the least, you can control destination order, deciding how data will be inserted in your cache if there are instances produced by multiple writer. And in that case, or the same instance produced by multiple writer, that's really when it gets interesting, because if you have synchronized clock, then obviously you want to order this based on source timestamp, but if you don't have synchronized clock, you can still introduce them based on reception timestamp. But watch out, because that has implication on eventual consistency for the system. Okay, let's look now at how this QoS compose and what are the 3 most relevant, I would say, or 2 or 3 most relevant QoS modeling idioms. So first of all, in any DDS system, you have to, at a very coarse level, try to identify what represents the state of your system, okay, and what are events. By the way, some people make confusion between state and event, but they are very different. So if you think for a moment mathematically, a variable that represents a state, it's always there. So it's a time continuous function. Okay, so I'll give you an example. If we think about the temperature of Earth in your room, okay, or on the planet, that's an example of a state. Okay, you can read it at any point in time, and you can think of it as a function that is continuous in time. Events are discrete function. Okay, so if I say the happening that the temperature is, let's say, greater than 25.5 degrees Celsius, that's an happening, that's an event, and it's true at a specific moment in time. Okay, so if you are able to understand what represents events and what represents state in your system, then you can use QoS to actually model them properly and capture the non-functional that are necessary for these different kinds of data. So even between states, you can distinguish between soft state and hard state. What is soft state? Soft state is a state that is periodically updated. For instance, data produced by a sensor. Okay, it's an example soft state. So when you're using DDS, and you want to represent some soft state, obviously you define some topic that represent the information, and then let's say the set of QoS that you have to care about are reliability, durability, history, deadline, latency budget, and destination order. What you want to use in this case is best effort reliability, volatile durability, keep last n for history, where typically n is 1 in most of the cases. But again, if you want to do filtering on this, you would set n to the number of taps in your filter. Your deadline would be the same as the update period. The latency budget, as a rule of thumb, you can set it as 1/3 the update period. And then you want to use a source timestamp if you have multiple writers per instance. For hard state, and hard state is state that is sporadically updated or that has temporal persistence requirement. Okay, so this could be, for instance, your robot configuration, a price estimate that takes 2 hours to calculate, for instance. Okay, so the QoS combination that are relevant for hard state are the following. So again, reliability, durability, history, destination order, and writer data lifecycle in this case. So what you want to use is reliable QoS, transient or persistent durability, keep last n history, and typically n in the vast majority of the case equals 1 in this case. Destination order set to source timestamp if you have multiple writers for the same instance, and then the write data lifecycle should be auto-dispose and register instance as false. Why? Because by default this is set to true, and if you want this information to be maintained by DDS durability service, when that is set to true, once you dispose an instance, well, let's say not, the problem is that disposal is automatic. Once you terminate the writer, the data will be garbage collected, and this is not what you want. How do you represent events? Well, again, an event in a distributed system represents the occurrence of something noteworthy for our system. Okay, a collision alert, a temperature beyond a given threshold. Okay, so the QoS combination that you have to set for event are, again, reliability, durability, history, destination order, write lifecycle, and resource limits. And what you want to have is reliable reliability. Durability really depends on your system requirement. Keep all history. Source timestamp for the destination order, it's sufficient. Okay, and again, you don't want to have you want to disable the auto dispose of unregistered instances, and then it's always good, as we are using keep all history, to define resource limits to essentially bounds the amount of memory that you might use. It's now time to look at some performance, and we'll do that again in the context of Cyclone. So Cyclone is one of the top performing DDS implementation on the market, and as you see on contemporary hardware, it delivers a latency that can be as low as 20 microseconds and that grows quite slowly with the size of data. I think it's also important to see that the distribution of this latency is very compact. In other terms, there is very low dispersion, as you can see from this diagram, where we are showing the minimum, the median, 90, 99 percentile, and also the max. So that really should give you an idea of how tight is the distribution latency. For what concerns throughput, very good level of throughput delivered by Cyclone, and I think the key point is to understand that here on a gigabit network, it's saturating a gigabit network starting from roughly 1 kilobyte payload. So it's time now for our Lab 2, and I'll show you how to do some performance evaluation with DDS. Let's now look at how we can measure DDS performance. So what I have here is I've cleanly checked out Cyclone. So let's build it. So that way you will also see how straightforward it is to build. So again, we configure the build system and then just make it. It will take a few seconds to build actually. And once it will build a series of examples some basic throughput and latency test, as well as a DDS benchmarking tool, which is called DDS Bench, which is what we are going to use to actually test performance. So you can use that DDS Bench to run both latency as well as throughput test. All the executable, as we will see, will be installed under the bin directory. So here you see everything has been built. If you look under bin, you see that among other things, there is the DDS perf, and it is sufficient to run the DDS perf to print its help. And you see here some example of usage. Okay, so as we keep the example of usage, what we can do, we can open, let's say, a few tabs, which I'll keep side by side so you will be able to see the result. And let's say, let's do a basic DDS throughput. Okay, so what I will do, let's start the DDS, so bin DDS perf sub, so that's a subscriber, and here we start the publisher. So DDS perf, and let's say pub, and the size, yes, okay, fine, 1 kilobyte, okay. So here you see that the statistics are being printed, and you see, for instance, that in this case, my subscriber is receiving around 3 gigabit of data per second. If we want to run a latency test, you see that, for instance, you can do here DDS on the receiving side, so bin DDS perf pong, and in here we do DDS perf ping. And again, it will start measuring latency, and you see on this case, on the ping side, that is measuring a latency of about 60 microseconds on my machine. Okay, so well, I mean, I think it's very good to have a way of measuring performance, and these tools help you very quickly and effectively actually build and measure some relevant latency and throughput. In this course, we have used a basic DDS installation, an editor, and a console to write, build, and run DDS examples, as well as the little performance benchmark. You could do the same by using the ADE environment, which was introduced in the first lecture and will be used for the rest of the course. There are instructions that were already provided on how to install ADE, and obviously from ADE you can also install DDS. You should also be aware that DDS is already included as part of ROS, and on this page, so index.ros.org, you can find information on how to select Cyclone as your default DDS implementation, or perhaps, let's say, some other DDS implementation. We are now to the concluding remarks, and I hope that this quick course on DDS was interesting for you. But more importantly, I hope they realize that DDS provides you with some set of extremely powerful abstractions, as well as mechanism for designing data sharing in large-scale distributed system. DDS is a natural fit for a very large class of distributed system, and specifically for robotics and autonomous driving. If you have any question, do not hesitate to contact us, and enjoy the rest of the course. Bye bye. Ciao.